Hi everyone, and welcome to another mini course at Physics Latam. Today is the first lecture on this mini course on Chern-Simons theory and invariants with Professor Pichai Ramadevi. She's a mathematical physicist and a professor in the Department of Physics at the Indian Institute of Technology, Bombay. Her research focuses on Chern-Simons field theory, knot invariant, string theory, supersymmetric Weaver theories, and the ICTP correspondence. I met her in India 2 years ago, and by then I invite her to give this series of lectures. So I'm very happy it's finally happening. And now I'll leave you with Pichai. Please go ahead.
Yeah, thank you, Daniel. I'm very happy to give this lecture. And yeah, stop me or Daniel can interrupt because I'm not able to see the screen who is showing hands, but you can interrupt me and ask questions. I can get to the board if required and show you the steps, whatever is required. Okay. So let me start giving you, since it should be pedagogical, assuming that there are a lot of, master's students, undergraduate students. I've kept it at a pedagogical level, but if you feel it is still not clear, please, interrupt me. So I work in IIT Bombay. I'm in Department of Physics. And this is my first lecture. And the other two will be on Thursday and Friday. So broadly speaking, this area in which I work involves quantum field theory plus adding topology in low dimension. Okay. So this together is now famously called as quantum topology. This area has become very well known now. It's a meeting ground for both mathematicians and physicists. So in the light of lot of interesting works, even the Nobel laureates, which have got for machine learning, this area is calculable. So a lot of data we can produce and many conjectures and open problems in this field can actually be, you can use some subset for training, which is what is required in machine learning neural network approach, and then validating or disproving or proving conjectures. So in that sense, it's been very topical that even though this area started in 1980s, late 1980s, now with this combination of exploiting topology and quantum field theory, which is quantum topology, has opened up a new arena where a lot of work is going on in this field. If there are many students here, you can take a look at one of a recent paper with Mark Hughes and Vishnu Janjala, where we use many data of knot polynomials to prove certain conjectures or get insight into conjectures. Okay. Okay, so to start with, I would just put a picture that you all know that these two are topologically distinct. One is what we call in mathematics as a two-sphere, denoted by S2. The other one has a genus 1, is like the surface of the donut, not the interior part of it. This is what we call it as a two torus. And interestingly, by pushing, pulling, or squeezing without cutting or snapping, you'll never be able to equate the two sphere to the two torus. So these two are topologically inequivalent. That's what I mean. And you need a mathematical quantity. This is, you can see it by qualitative argument that these two are inequivalent, but you need a mathematical quantity to say that these two are actually inequivalent. And interestingly, it is known that there is a quantity called Euler characteristic for two-dimensional surfaces, where you can triangulate these surfaces and look at the number of vertices on the triangle, edges and faces of the triangle. And you can compute, after you've triangulated the whole surface, if you compute them, then you will get this value. And that value for the sphere will be 2, and for the torus, it will be 0. So genus 0 is the two sphere and genus 1 is the torus. Okay, so this is a nice mathematical quantity which actually distinguishes topologically inequivalent two-dimensional surfaces. Okay. Now, if we go to 3 dimensions, a 3 manifold, do you have or do we have a mathematical quantity which should say that, those 3 manifolds, manifold 1, manifold 2, they are topologically inequivalent? Can I find a mathematical quantity? So this is an open question, and which kind of being, for example, I'm listing a couple of 3 manifolds. This is the extension of the 2 sphere to a 3 sphere, just like circle can be extended to a 2 sphere, 3 sphere. Then you can also have a 2 sphere tensor product with S1 at every point on S2. So that is also a 3 manifold. You can also have an S1 cross S1 cross S1, but you can also, quotient it by, some discrete groups, which gives you some manifolds like, lens spaces. So there's a whole list. I've just given you a few examples. Can we find an analog of this Euler characteristic quantity for such manifolds? Because these I know are inequivalent, we should find the quantities which are different for different 3 manifolds. Okay, that's the main motivation. And further, 3 dimension is very special, especially S3 can be viewed as if you are looking at R3 with all points at infinity identified, just like you do in S2 to be R2 with all points identified. The simpler problem is that in 3 dimension, you can have non-trivial objects, loops, which is non-intersecting curve in 3 dimension, which you can project it on a plane, but when you project it on a plane, you put an overcrossing or an undercrossing. Okay. So these are non-trivial objects only in 3 dimension. If you go to the 4th dimension, you can make everything look like this simple loop. Are you able to see my mouse? Yeah. Yeah. So these are non-trivial objects in 3 dimension. Why I'm bringing this non-trivial object is, first, to get the quantity associated with the 3 manifolds, I want to first get the quantity associated with these simpler non-intersecting curves in 3 dimension, especially in S3. And then there is a procedure, okay, to convert, there is a procedure called surgery to take such knots, surgery of such knots in S3 can actually give me the other 3 manifolds. So it's a very systematic process. So the simpler objects, if I can distinguish, then I can go to the next step of doing the surgery and find out the 3 manifold quantity associated with 3 manifold. Okay, so this is for non-intersecting curve. You can have non-intersecting many curves which are entangled. That is what I've shown it on the right-hand side. So this one is what we call it as a Hoff link. Then there is some Whitehead link and so on and so forth. And I've also added more additional information that you can give a crossing sign depending on keeping your forefinger on an overcrossing and seeing how the orientation of the other curve at the overcrossing, okay, goes, and then you can give a sign to it. So here, if I try to do that, I will find that it is a negative, negative handedness. So then the sum of all these at every crossing, we take the signs and we add up, and that is what we call it as a right. Okay, sometimes you call it as a crossing number. So trefoil has a right -3. Some conventions we follow. So this is what we call it as a left-handed trefoil. Some books calls it as a trefoil or trefoil star. So we just systematically follow that. Given this diagram, the right is -3. And similarly, you can go to one more crossing, which is what I've shown here. You can play around by putting your arrows and look at how the arrow signs are. 2 of them will have positive signs for the right and 2 will have negative, so that the net right for this diagram is 0. So this diagram is what we call it as a figure 8. Okay. So unknot is the simplest curve, but then there are non-trivial curves, and these two cannot be equivalent because you can't pull and push to make unknot to be equivalent to 3-1, which is trefoil, or you cannot make it equivalent to 4-1. Okay, so this is a very systematic tabulation with slowly increasing number of crossing numbers. So this is 5 crossing. This is also another 5 crossing, but inequivalent to this 5 crossing knot. So that's why they get an additional, address to it. 5 subscript 1 is for this knot, 5 subscript 2 is for the other knots, and so on. Okay, 6 crossings. 6 crossing also has many knots. I have not drawn it here. Similarly, 7 crossing has 2 knots. Okay. Okay. And similarly, when you have two entangled curves, then you can start looking at objects like linking between those two entangled curves. So that's where the linking number comes into play. Okay. So in knots, you are only worried about crossing number or right. Whereas in links, you can look for linking number between components. And you clearly see that the crossing number, this also has 5 crossing number, this one is also having 5 crossing numbers. Similarly, this has 7 crossing number, this is having 7 crossing number. In some sense, two inequivalent objects share the same crossing number. So we sometimes say that the crossing number is a very weak invariant. Okay, it can distinguish trefoil from figure 8 or 4-1 from 5-1, because the crossing numbers are different. But 5-1 and 5-2, if you take the mirror image of this, those two will have the same right and the crossing number, but I know they are topologically inequivalents, but they share the same crossing number. So in that sense, we call this mathematical quantity to be a weak invariant. Similarly, linking number also, this linking number between component one curve, which is this, and the other curve, it turns out to be 0, but you can also put two loops which are not entangled. That is also linking number 0. So linking number is also not a very good invariant, but definitely for some examples like this Hoff link and Whitehead link, you can actually show that their linking numbers are different, so they are topologically inequivalent. Okay. So this is just to give you a motivation that our aim is to find a mathematical quantity for these simpler objects, not crossing number or linking number. Of course, we should find in physics, in a quantum field theory, is there a formal way of defining expectation value of an operator which corresponds to an observable, which is the crossing number or linking number. I'll come to it, but that is the motivation. Okay. Now I'm going to just confine to knots. As I said, once I know knots, I can get more information about three manifolds. So, and independently, knot theory per se has a lot of tentacles. Okay. So this is a branch where many areas interact. And I would strongly ask you to read this book by Colin Adams, where there are many applications. Theory as a main lifeline, but within physics, we have exactly solvable models, quantum groups, Chern-Simons field theory way of looking at knot theory. Computer scientists are interested in looking at complexity issues of various problems, like how many scissor cuts are required to make a complicated entangled many curves to become simple single loops. So they do relate it to satisfiability, or 3-SAT problem, or NP hard, NP complete kind of issues. Mathematicians, of course, have been working on knot theory even before, in the last 1 century. So they have been looking at formal aspects of topology. Chemists have been looking at, knotted structures, stereoisomers, synthesizing molecules. Of course, biologists look at how the knots happen. Knotting happens at a synaptic node when they inject an enzyme, and they give this enzyme action to make it knotted like a trefoil and so on. There's some work on this tropoisomerase and all. So there's a lot of interesting areas in which interdisciplinary and interdisciplinary, where knot theory seems to be playing a very important role. but I will confine myself to connections to Chern-Simons field theory in this talk. But this just to give you a broader feel. If anybody is interested, can look into many of these things. Okay. And what exactly we want to see from physics before we start looking at from physics, we should also know what are the salient features of knot theory. Okay. So first of all, if I give you a simple loop or a loop of this type, okay, you can see that very clearly this self loop can be removed, right, in 3 dimension, because we are not on the plane, we are in 3 dimension. So these two are actually equivalent, okay. So by pulling and pushing in 3 dimension, these two knots, this is a simple unknot. This object which doesn't look like an unknot is actually an unknot. So these two are equivalent. But if I give you a complicated object, okay, very complicated object, I tell you that these two are equivalent, but you have to do a lot of hard work to actually push and pull and see whether we can get back this, okay. So we need a systematic set of rules to show this A is equivalent to B or A is not equivalent to B. Okay, suppose I say that A is equivalent to B, I need to propose a set of rules and apply the set of rules on this A and see whether we get B. Okay, so those were proposed by the famous Reed master. Any region, you go and look at a specific self-crossing. This is what he calls it as Reed master. In the literature, it's called Reed master move 1. You can unwind it and make it like a straight line. Other cases, both of this curve is going over the other curve. Okay, you can actually slide it. Similarly, here, I can take this strand and slide it below, which is what is done. These are the 3 moves you are allowed to do. And by doing these 3 moves any number of times in any of the regions of a given knot, and if you are able to go to the other knot, then you say that the knot, a given knot is equivalent to the other knot. Okay, this is what is knot equivalence. Okay, so what do we mean by now, given this equivalence, you have to define a quantity for these knots such that the quantity is different for trefoil from unknot, different for figure 8 and so on, okay? So mathematical, just like we did this Euler characteristic, you need a quantity such that they are same for equivalent knots, but they should be different for inequivalent knots. So then you call that quantity to qualify as a knot invariant. Okay. For instance, Jones proposed a nice recursive equation, recursive relation or Skene equation. Basically, let's look at the trefoil. You confine yourself to looking at a particular crossing. Okay, so this is overcrossing, this is undercrossing, confined to look at this particular crossing. Make that particular crossing to an undercross. Okay. Other possibility is keep the directions of the arrow and make that particular crossing to be a no crossing. Is that clear? So I'm going to denote this specific overcrossing by an L plus. I've shown it for an example, but in general, you can concentrate on a particular crossing and call it to be L plus. Convert that particular crossing into an undercrossing, call it L minus. And the last one, which is L0. These 3, the invariants, the quantity which we write, between these 3 nodes are related by what is called as a Skene relation. Okay, so I've formally written J of L plus, Jones polynomial is what we call it. Q, the polynomial is in variable Q. So this is the relation which this 3 will satisfy, and we can compute them. Okay, as an exercise, I would urge you, for example, you can see here this diagram for the trefoil. When I made it into a no crossing, this diagram is actually a half link. This one, once I made it under crossing, can you see what it becomes? You can use the Readmaster moves because two consecutive overcrossings can be removed and you can make it an unknot. Okay, so this is trefoil, this is unknot, and this is half link. If you're not able to see it, please play around on your notes and check that this is actually an unknot. Okay, so you need to write the Jones polynomial for a trefoil in terms of Jones polynomial for an unknot and a Jones polynomial for a half link. Okay, so that is what I've done here. And we are going to assume a normalization, at least Jones assumed a normalization, where he took for the unknot to be 1. But if you have two simple unknots, disjoint unknots, then that polynomial, he took it to be q power half plus q power minus half. So we're going to use this normalization and do an example now and see how we get this polynomial. Why I'm stressing this? Yeah. So when Jones introduced Q is just a variable, has no physical meaning. But when we do the Chern-Simons theory, Q gets a meaning for it. Okay, so we'll see that. Any other question? Okay. So right now Q is a variable and the quantity which associates a not invariant is in variable Q. Okay. Let's do this example clearly now in the next slide. And then that will clarify how to go about it. After this, I want you to do as an exercise for a figure 8. Okay. Please try and do the similar exercise by taking the figure 8 diagram, concentrate on a particular crossing, make it into a no crossing and under crossing, and redo this calculation and let me know what is the polynomial you get, okay, using the skin relation. I will do it now for the trefoil as a warm-up and I leave it you to do it. Why I'm trying to do this is that Witten in 1988-89, he actually showed in quantum field theory, which is Chern-Simons field theory, this skin relation can be reproduced. That is why I'm trying to stress that Jones polynomial historical work in the context of knot theory, that Witten could actually reproduce the skin relation. Okay. Any other question? Okay, so just as an example, I am trying to redo this. Only modification I've done in this, I've used here Q inverse, but I can scale it also as Q squared, Q minus 2, just to make this look a little better. So I can promote this Q to the half as a new variable, which I'm calling in the next slide as Q. So this is just a change of variable I've done here. Okay. No, I've not done any change of variable. It's the same. Okay. Sorry. Yeah, just redo it using this in the evaluation for the trefoil. Okay. I'll leave it you to do it and see that you end up getting. See, if you see here, it is a half link, as I said. Again, you concentrate on one particular crossing and rewrite that particular half link in terms of no crossing and undercrossing. If you do an undercrossing, it becomes an unknot. But if you do a no crossing, it will become two unknots and use the fact that two unknots is q power half plus q power minus half, and you'll end up getting this polynomial. Okay, I'll leave it you to check this and see that this is the procedure of getting the polynomial for every knot. Okay. Any questions? Okay, as I already said, why we went through this, we will see it in the next lecture. about this, that Witten obtained the same skin relation using Chern-Simons theory with the gauge group SU2. So sometimes Witten's work is also said as a three-dimensional definition of knots and how these invariants are obtained in the quantum field theory as expectation value of observables in the Chern-Simons theory. So it's very beautiful that one could get these invariants in a quantum field theory, which is Chern-Simons theory. Okay. The other feature in the salient aspects of knot theory is knots can also be obtained from braids. Okay, so technically Alexander's theorem says that a closure of braid gives you knots. I will try to pictorially show you how this line can be understood. Okay, so I am going to briefly tell you the group called braid group, and the subscript n denotes the number of strands. Okay, you can take various strands. Here I've taken n strands, and I can evolve in time with no crossing between them. This is what is sometimes called in the group. In every group, you need an identity element. So this is an identity element. Of course, you can exchange between the ith strand and I plus 1 strand, which is what is called as generator. And there are many generators. So you have n minus 1 generators here. Using these generators, you can construct words. Okay. So this is one example where I have constructed B1 squared, the first and the second strand twice, and then B2 squared between second and the third strand twice. So this is what is a general braid element belonging to Bn. Okay. So if you are just looking at 3 strands, then this belongs to B3. But this is the braid word which is constructed using these generators. Okay. And forms a group. It is not a free group. It is actually subjected to a defining relation. If you exchange between I and I plus 1 and j plus 1, which is not neighboring strands. So if I do between I and I plus 1 and then do I plus 2 and I plus 3, the order really doesn't matter. You can see that it is commuting. But if they are consecutive, bi plus 1 bi, it is going to satisfy this restriction. Okay. This restriction in some sense is similar to the Reidmaster move 3, but there I drew a different diagram, but you can redraw this and show that it is looking like the Reidmaster move 3. Okay. So it is not a free group. It is subjected to these two equations. So it is going to be still a group subjected to these equations. Okay. And why I said Alexander's theorem is the closure of a braid gives you a knot. To see the closure, you just identify the final. If I take this to be evolving in time, the final time state you identify with the initial time state. So that I've shown it by the dotted line, the strands are identified. Once you identify them, it becomes a knot. So that is what I mean by a closure. Sometimes in quantum physics, we will say it is a trace operation, and this will give us a arbitrary knot or a link depending upon whether it's one non-trivial curve or many entangled curves. Okay, is that clear? Any questions? Okay. Okay, so then the next question is that just like Reidmaster moves, where you can do a set of operation to go for equivalence thing, the closure, the trace, like if you take this
How is closure cell is tracing?
yeah, so I'm just trying to say it's identifying the initial state with the final state. Okay, if you do it in quantum mechanics, when you identify an initial state to final state, you take it as an expectation value. And if you try to write those states in terms of the basis states, it will turn out to be that, they are like doing a tracing over all the basis states. Okay. So I'm just giving you a very formal way of looking at it. Oops. So this thing which I'm saying is formally, the closure is pictorially shown here, but we will see that this closure can be seen as tracing. As I will tell you the Markov move, where you will see that it is actually looking like if you had two matrix representation. See, for example, if you take A and B as some arbitrary braid word, you can either close, when you do the closure, it doesn't care whether A was in on top or A was in the bottom. Okay, in some sense, if you had written a matrix representation for A and B, trace of AB will be same as trace of B. In some sense, the closure can be viewed as a trace. Okay. So this is what we call it as a Markov move 1. Okay, this as a braid word, B followed by A is different from A followed by B. But as a closure, I could have started from this line and gone to this line, or I could have started from this line and gone to this line. It doesn't really give me a new knot or a link. It gives you the same knot or link. Okay. Another thing which I can do is I can take a braid word A. I can add a one more strand and put a twist. Okay. Or I can put a undercrossing twist. These as a braid word in this braid group, it is going to be different. But when you close it, the extra closing, the readmaster move 1 will play a role, and you can remove it and make it look like the closure of the braid word A alone. Okay, so this is something which you can see that as braid words, they are different, but closure gives the same knot or link for both Markov move 1 and Markov move 2. So what is the strategy when I want to construct the knot invariants using a representation for these braid generators? That is what I should know. First of all, you have to construct a representation for these braid groups, define an operation, I'm calling it as trace, such that that invariant which I'm writing should not change under Markov move 1 and 2. Then they qualify to be a knot invariant. Okay. Otherwise, it is not a knot invariant. Okay. Just to give you a flavor, all the knots which I showed in the earlier slide, you can redraw. Here I've drawn this trefoil as a closure of a two-strand braid. In figure 8, I've done partial closure and a plait. Okay, so sometimes it is called as a quasi-plait diagram. This is also a closure. This is a quasi-plait diagram, and so on. So you can try and redraw every knot which is given in the knot table, which is Rolfson table or Thistlewhite classification. In redrawing it as a closure of a braid, every knot can be drawn as a closure of a braid, but sometimes if you want to keep the number of strands to be very small, we play around by drawing a quasi-plait diagram. Okay, so here if you see the number of strands looks like as if it is 4 at every stage. If I take a cross section here, all of them have 4 punctures on that cross section. Okay, so that's the usefulness here. So, and it helps in, because they are all useful to do the computation of knot invariance if I can redraw it as a quasi-plait diagram. Okay, with minimal number of punctures. When I take a cross section, there's only 4 punctures here, and very easy to compute things. Of course, you can redraw them by many number of strands, then the computation becomes a little more complicated, but it can be done. Okay, what is the essence? Essence is that whether I draw a trefoil of small size or a bigger size, or a figure 8 a small size or a bigger size, it doesn't really matter. Topology is same. Topology of a trefoil, whatever be the size, it is the same. Similarly, the figure 8, the size really doesn't matter. Of course, these two are inequivalent. Trefoil is inequivalent to a figure eight. So you need a theory where the notion of size, big size or small size, should not matter. What does that mean for us as physicists? It means that you should not have, any size or length change is dependent on metric. So observable, which is given by an expectation value of an operator, if you do a metric variation, which will see the size, that should be zero. Okay, so that is one of the constraint. Metric variation of expectation value of an operator must be zero to qualify as a topological invariant. It should be same for this or this. Okay, similarly, should be same for this or this. So such a quantity we should be able to write. Is that clear? So, and the broad quantum field theory, which captures, it doesn't see whether it's small or big, those are what we call it as a topological quantum field. Okay. Okay. So I'm now confining now. So far, I've given you salient features of knots. I've tried to tell you braid groups. And I've also said that one is interested in finding braid group representations. And we will try to find those within a topological quantum field theory, which is a Chern-Simons theory. But let me first give you the background of topological quantum field theory before I get on to Chern-Simons theory. Okay. So topological quantum field theory is useful to study geometry and topology of low dimensional manifolds. So by low dimension, I mean it is mainly used to study 3 and 4 dimensions. Okay. And these are the theories where you can show that T mu nu can be written as variation of action with respect to metric. And because it's topological field theory with no notion of, small or big size, the energy momentum tensor should vanish. So no dynamical degrees of freedom. And clearly, the operators whose metric variation is zero, they are what we call it as topological invariants. Those expectation values of those operators which satisfies this constraint, these operators are supposed to give us information of a quantity associated with objects, the topological objects like trefoil or figure eight in 3 dimensions. Okay. Okay. So I also want to give a brief, literature available. These are works of Witten in 88, 89, where topological quantum field theory is broadly classified into 2 types. One is cohomological or Witten type, the other one is Schwarz type. Interestingly, the cohomological type is what can be used to explain the Donaldson 4 manifold invariance. And Schwarz type is what is going to give us a natural scenario where we can study knots, links, and 3 manifold invariance. And to give you a quick info, you can write the action here. Sometimes we say that the action is BRST exact, where it is, the variation with respect to the Q, which satisfies Q squared equal to 0. Okay. And all the operators should be BRST closed. They have to be 0, but it should not be BRST exact. Okay. So this is what is the crux of cohomological Witten type invariance, which I'm not going to get on in the rest of the talks. But anybody is interested, there is these 2 classes of topological field theories. Schwarz type is what I'm going to confine. In the Schwarz type here, there is manifestly, it's not metric independent action. It can have metric dependence. But what you will see is that any variation of expectation values of observable with respect to metric will be 0. Okay. So in that sense, this is not manifestly metric independent, but here we explicitly put the action to be metric independent. Okay. And operators also we choose to be explicitly metric independent. Okay. And to give you some more detour on historical remarks, what is Chern-Simons? Okay. Two mathematicians, Chern and Harris Simon, introduced this three-form term in the action. Okay. And this theory was first discovered by Albert Schwartz. That's why it's called Schwartz type. And this three-form term was introduced by Chern and Simon. Incidentally, I don't know how many of you know the Simons. Recently, last year, he passed away. And he is the founder of that Simons Foundation, who has been funding many of the, you might have heard about the Simons Foundation. Okay. So three form, which I was saying, introduced by Chern-Simons. So anytime, any field theory, when we start, we have to start with giving an action. And then this is the path integral of the action. So this is a gauge theory. So this path integral is over all the gauge fields modulo gauge transformation. And this object was what we call it as a generating function or the partition function. Okay, and it was, I put the Witten's picture. So Ed Witten used this to show how this theory provides a natural framework to study knots and links in Chern-Simons theory. Okay. Okay, formally I have written Z of M3, but if you could compute this Z of M3, this will capture the topological information about the three-manifold M3. Okay, so this M3, as I said, all these theories are valid in 3 dimensions, and this action which we are taking has to be integrated over the 3-manifold. Okay. Yeah, so formally I should have said Lagrangian density and integrated over the 3-manifold. Okay, that is what is the action. So Z of M3 is the topological invariant, and if we can compute, then you can compute for different 3-manifolds, and then this quantity can be treated to be analog of your Euler characteristic for 3-dimensional manifolds. Okay, there are a lot of works where by surgery you can obtain these 3-manifold invariants up to some normalization constant. In the literature, you would have heard words like WRT, Witten-Reshtikin-Toraev invariant. So the partition function in Chern-Simons theory is related to is up to a normalization related to WRT invariance, which mathematicians keeps using at WRT invariance is what they say. Objects. In any field theory, you have to start listing out the observables. Observables should be metric independent. Operators associated with it should be metric independent. And we want to look at expectation values of such operators associated with this to give you the not invariant for trefoil, not invariant or link invariant for Hopf link, and so on. Okay. So there is Wilson loop operators, which are explicitly metric independent, and we can take expectation value in such a theory, and we can obtain the quantity, which is called as a knot and link invariance. Okay. Okay, so as I promised, I want to take few minutes now and look at this abelian Chern-Simons theory. Okay, to explain what quantities this abelian Chern-Simons can compute. Just like any gauge theory, the action for this abelian Chern-Simons is explicitly metric independent because this is totally antisymmetric. You can't have any metric dependence. And K is the coupling. And if you insist on looking at gauge invariance, you can show that k can shift up to integers. So it has to be, k has to be an integer. Okay. So this is one of the requirement. And take this action and find the propagator for this action. I'll leave it to you as an exercise to find the propagator for the action. So gauge invariance, as I said, will require k to be an integer. Please work this out. I'm not going to do it in this lecture, but take this action and work out the 2-point correlator and show that the 2-point correlator has this form. Okay. Why am I doing this? This will come into picture when I work out expectation value of the Wilson loop operators in this abelian Chern-Simons. Okay. So what is the Wilson loop operator? It should be gauge invariant and metric independent. A mu dx mu formally is gauge invariant, and the exponential of this will be metric independent also. Okay, over this loop. So this is a very good candidate to be associated with every not k, and this n is, I have to put an n here. I missed the n here. N keeps track of the abelian charge. Okay. And for links, you will have many such curves, as I said, entangled or not entangled. And you have to take a product of those curves. Okay. So this is what is for the links. What I'm trying to push is that these expectation values of these Wilson loop operators, when I work it out, they will capture the crossing number for a knot. Similarly, if I look at a link, they will capture the linking between different components. Okay. And this can be systematically worked out. So, and that was cost linking number, and use the 2-point correlator, which I showed you in the previous slide, which I brought it here again. And you can work out the expectation values of these two loops over curve K1 and K2. And this integral form is what is called as a Gauss linking number, and it is a number, okay, which I formally showed you how to find the linking between various components, how to find the right in the earlier beginning of the talk. And what I'm trying to show is you have to take an exponential of this piece and an exponential of this piece to compute expectation values of link operator, or the K1 and K2 can be same if you are looking at exponential of a Wilson loop operator associated with a knot. But when you do it for knot, you have to do carefully what is called as a point splitting regularization, where you take K2 to be slightly shifted from it, do it as if it's a linking between the knot and a frame, and then compute the self-linking number or the crossing number. Okay, so these are the systematic exercise one could do in abelian Chern-Simons theory, and you can get explicitly the linking number for links and crossing number for knots. So what is the upshot of what abelian Chern-Simons theory can achieve for us? Abelian Chern-Simons theory cannot give any more information. It can only either capture the linking number or the crossing number. Okay. So abelian Chern-Simons gives crossing numbers and linking numbers. And we have seen that the crossing numbers and linking numbers are weak invariants. Correct? So we need to go beyond abelian Chern-Simons theory if we want to capture. If you saw the 5 crossing had 2 such knots, 7 crossing had 2 such knots with the same crossing number. If you want to distinguish it, expectation value of that 751 or 52 would have given you the same crossing number and linking number in abelian Chern-Simons. So we have to go to non-abelian Chern-Simons to capture those information. Is that clear? Okay, so just to flash you, if you go and look at knot atlas, they have put in all these knots. You know this periodic table in chemistry, right? People have hydrogen, helium, lithium, dot dot dot. Similarly, you have this periodic table of knots. Okay. So if I say lithium, people all understand Li is lithium. So any knot theorist, if you say phi 1, they know what knot we are referring to. If you say phi 2, they know what knot we are referring to. So they are like analog of your chemical elements notation, but in the knot theory context, this is a knot theory table. Okay, knot table. So knot atlas has tabulated. What is the open question? All of them are knots. Okay, I need to find expectation value of a Wilson loop operator with certain charge. The charge depends on what gauge group I'm looking at, what representation of the gauge group I'm looking at. Is this one-to-one on 2? What do I mean by that? If I work this out for trefoil, if I work this out for figure 8, I want their answers to be different. In fact, every answer, they are all topologically inequivalent. I want this invariant on the right hand side for each one should be distinct. Then I have achieved classification of knots. Like in the periodic table of chemical elements, every element has a different atomic number and an atomic weight, right? That set is different. That's why it's all those elements are distinct. Similarly, I need to find this expectation value to be distinct for each of them. I know by drawing they are not related by read master move 1, 2, or 3. They are all inequivalent. I need to solve this. This is still an open question. Okay. It's still an open question. Many of us have been working for more than 2 or 3 decades. We have managed to improve the classification, but complete classification is still an open problem. Okay. So if you come up with 2 knots, yeah. So what is he asking? We are calling Yes, definitely. Yes, because you're not putting it as a matrix valued. So A mu, Nu commutator will be 0. Okay. Yes. Is that all right? Can I proceed? So Chern-Simons improves classification. That is where I have played a role in the last 3 decades. But still there are issues in some examples. Okay. So we need to go beyond abelian Chern-Simons if we want to attempt classification of knots, not just looking at crossing number or linking number. And that's where non-abelian plays, as someone asked whether they commute. For a non-abelian group, you can take it to be any compact semi-simple group. The reason is that K, I want it to be integer, positive integer. And this non-trivial element would have been 0 in abelian theory because they commute. Okay, here it is non-trivial. They are all matrix valued in this, valued in gauge group G. Is this clear? You've all done Yang-Mills theory, right? You have done electricity, magnetism, which is Maxwell's theory. Maxwell's theory is abelian, where the gauge field is only one unique gauge field. But when you go to SU2 Yang-Mills, you start getting gauge fields don't commute. It's the same thing here. So you can take the G to be SU2 for simplicity, but this is what happens. Okay, I'm not keeping track of the time. Probably I have still another 5-6 minutes. Can I complete the slide, Daniel? Is that okay? Yeah, I still have time, right? Yeah, okay. Okay, I somehow thought it is. Thank you. Okay, so the first thing I want to do is, just like in any non-abelian theory, I would like to first write an interacting vertex, right? So that's not very visible here, but you can do a rescale. You can do a rescaling of a mu by a lambda factor where lambda is related to k in this fashion. If I do this rescaling, we end up getting the action, the above action rewritten in this fashion. Is that right? So now you can see that this is like the interacting piece with the coupling constant lambda. This one is without any coupling. This one has the coupling. Okay. This is what you do in any field theory, phi cube theory, phi 4 theory, Yang-Mills theory. You keep the kinetic term, you say, but here the kinetic term is not quadratic in the derivative. In 3 dimension, you have only a single derivative term, but it's quadratic in the field. Okay, so in that sense, you can call it to be a kinetic term, and this will be the interacting vertex term. Okay, so what do we do if we have such a term? This term we did not have in abelian Chern-Simons theory. So we explicitly did the computation. Okay, if you know the propagator, we could actually do the computation for any Wilson loop expectation value easily. But once you have this interaction term, you can do only calculations order by order in lambda. Okay, so that's the perturbative Chern-Simons. We do perturbative term in lambda. It's a perturbative Chern-Simons. Okay, so what do we do in perturbative Chern-Simons? So we start taking this action, and clearly this epsilon mu nu lambda makes sure that the action is metric independent. No metric dependence, that is what we want. And we can find the expectation value of the Wilson loop operator for a specific knot k, which I take the exponential of a mu dx mu, which is a one form, and the loop is over the knot k. But you have to also do path ordering, and then you need to take the trace over a representation. So I'm going to work with some gauge group, semi-simple gauge group G, and I'm going to put a representation because depending on the representation, I will take the matrix value in that representation. Like for example, if I take SU2, if I put fundamental representation, then they will be A mu A polymatrices, sigma A. If I put spin 1, then it will be a 3 by 3 matrix representation, and so on. So this A mu matrix value depends on what is the dimension of this representation of the gauge group. And this operator will be explicitly metric independent and gauge invariant. And this can be worked out systematically in a perturbative Chern-Simons theory order by order. Okay. So I'll leave it you to do at least till order 1 and order 2 to get some clarity. Okay. And what will happen is that we will get a piece which is representation and group dependent. Okay. So this DI is for every order. There are some DI terms of this group. And it's also dependent on the representation. If I put a spin half for SU2 or spin 1, then this factors will be dependent on whether it is spin half or spin 1. And this factor is completely topological. Okay, this term is completely topological. The reason why it's completely topological is because it doesn't care about group or representation. It only captures the topology of the curve or the knot K. And this keeps track of the order at which we are computing it. And you have to sum up over all orders, and that should give me the expectation value of the Wilson loop operator. Okay. I've formally written this, but order by order can be done. Gudagnini has done this up to second order or third order for some simple examples. You can take a look at it. Okay, so as I said, this is a group factor and this is a topological invariant at the specific order I, and sometimes this is called as a Vassiliev invariant. The perturbative invariance which captures the topology, they're called Vassiliev invariants. Okay. Okay. Other thing which also you're familiar with in any field theory can be done here. Take the action, write the equations of motion for this action. You will see that the gauge field, non-abelian gauge field, will vanish. Okay. So the solutions to this vanishing non-abelian field strength, sorry, the gauge field is not vanishing, the field strength vanishes. The solution will be non-trivial field connections or flat connections. They're called flat connections. Anything, any solution of gauge field which satisfies F mu nu, the field strength being 0, is called flat connection. So the solutions for all the A mu depends on what manifold we are looking at. Okay, if you are looking at a manifold which is a S3, S3 is similar to R3 because R3 with all points at infinity is identified. Then the space of flat connection will only have a trivial flat connection. But if M is some non-trivial manifolds, then you need to worry about the fundamental homotopic group and they will dictate what should be the space of flat connections. Okay. So you can have more than one flat connection depending on what manifold you're looking at. And typically you say there's a solution to the field strength being 0 is a space of flat connection in Chern-Simons theory. Okay. And then what do we do? If you take a classical solution, which is this solution to this field strength being 0, you perturb around the classical solution and compute the first slide where I showed you that when I started with Chern-Simons theory, that partition function is given by the path integral over the space of gauge fields, modulo gauge transformation. And we take the action which is perturbed around the classical solutions. Okay. Okay, so this also I'm not really proving it for you, but one can show here that you can do one loop and explicitly check that you need to renormalize your K to K plus H. For SU2, H is 2, SUN it is N. It's called the dual coaxial number. So that's an effective action you can write. You can write it as e to the power of I S effective, but that S effective will involve a coupling which is shifted. Okay. Technically, in any field theory, if you do order calculations, right, like this previous slide which I showed you, this thing which I've written here, right, it's not at all clear that this is summable, okay? It's not at all obvious that you can sum up over all I and get a summed up quantity. It could blow up, it could be divergent, okay? Many field theories, the summation need not be a convergent series which gives you a finite summable quantity, okay? Interestingly, in Chern-Simons theory, this turns out to be summable. Okay? So that's why I've written the other expression here that you can finally write this whole summation, perturbative summation can be formally written as a quantity, some functional quantity which depends on the representation. It depends on the not k and the q variable which showed up in the Jones polynomial, which you are asking what the q variable is. In Jones, q variable has no meaning. But if I want to try and map things, I will show that the q variable is related to the Chern-Simons coupling and depends on the gauge group. It is the dual coaxial number. And interestingly, it is also summable. Okay. The only way I could verify or anyone can verify this is for some simple examples, the q variable, which is involving exponential of 2 pi I by k plus 2, k plus h, or if you take SU2, k plus 2, you can keep terms up to 1 over k and 1 over k squared and 1 over k cube. And this side, you can do loop calculations up to order 1, order 2, and order 3. And you can compare both sides and check that the results are matching. Okay, so that's the only way in which I could kind of convince you that these two are possible. But in general, doing all loop calculations, summing it up and showing this is not possible. But there is a independent way in which Witten argues that you can compute the non-perturbative computation of Wilson loop operator without going through these perturbative steps. And that involves redrawing every knot as a closure of braid, and how this can be done, where you can get this final answer in variable q, and that final answer in variable q can be compared with the Jones polynomial if you put the fundamental representation of SU2. Okay. Should I stop here or you want me to continue the next? Like for the index and power alpha, index and power alpha in the 2-point correlators, does it take all values 1, 2, and 3? Yes. Yes. Alpha has to be between 1, 2, and 3. Yes. Yeah. I thought the not invariant would not be computable if it were non-compact, non-semi-simple. See, not invariants are computed in the SU2 and compact semi-simple groups. But what you do for non-compact semi-simple groups is you kind of capture the volume of not complements as a leading term, and then you get those A polynomials where the space of flat connections cannot be, it is not that, it's very different. The zeros of the A polynomial gives you the space of flat connections in SL2C. So it's different in the non-compact SL2C and other non-semi-simple groups. That's that answer. Anyway, let me come back to this Orgelio question. Right? There go. Now I have to see how to close this. Yeah. So your question on this abelian, right? Yeah. So this mu and nu can be either 0, 1, 2, because we are going to always confine to 3 manifold M. Okay. So what will happen is that the mu and nu index are kept tack, and then this will be the alpha is summed up. Okay. But this should be totally antisymmetric. So if mu and nu are 1 and 2, alpha has to be only 3. Does that answer your question? Yeah. Any other question? Is this summable also clear to you? But formally, I'm writing it. I'm not giving you a proof. I'm only saying it as a data that this is what conventionally we do in any field theory, the perturbative analysis. But interestingly, the perturbative variable lambda, which is proportional to 1 over root k over all orders, if you can sum it, you can write that summed up value to be in a variable q, and that q is exponential of 2 pi I by k plus the dual coaxial number for SU2 is 2. You can expand it out and compare both sides. That's all I'm trying to say. Is that clear, Daniel?
Yep. Think
Okay.
so.
So now I'm just going to give you some kind of a trailer for the next 15 minutes. And then we can continue on Thursday on it. Okay. I kept the slides, but I will I was not sure whether the time will be sufficient, but let me put this in. So computation. So I'm not told you what is summable, but how it is summable, how do you get the F of R? But this requires two ingredients, this computation. One is, I've already told you the first ingredient, where every knot, you first redraw it as a closure plait or a quasi-plait diagram, which is what I've shown already to you. And then the next ingredient which you require is that you slice the knot inside S3. Okay, once you slice the knot inside S3, the manifold which we get will be an S2. So let me show you by picture. So take the S3. This is the trefoil which is drawn as a closure of a 3-strand braid. And I'm going to confine myself to an SU2 Chern-Simons theory. So this can be arbitrary spin representation of SU2. Okay. What I can do is I can slice this diagram into two pieces. Okay, I've sliced one upper piece and a lower piece, and I can glue it back along this boundary. The boundary is an S2 boundary with 1, 2, 3, 4 punctures. Okay, so this S2 boundary and this S2 boundary are oppositely oriented. Any questions? I do see a lot of questions.
There are two questions.
Yeah, let me open it. I think I. Yes. Since our theory is a topological field theory, changing our manifold M to some other topologically equivalent manifold should not change our result. How is this captured in the theory? How would the transformation work? My worry is that there is no metric in the volume form of the action. Sorry for asking this question a little late. Okay. And the next question is, why can we slice the diagram? Why can we slice the diagram? It's not clear.
So this not in S3 and you
I
are
think he's talking about the boundary, the S2 boundary.
Yeah, so you can do in various ways, but the simplest thing which Witten had done. What was the earlier question? I forgot actually. Yeah, so yeah, his question on Z of M being topological invariant, if I change it to some other M prime, will it change or not? Is the question, right? So we will see that surgery of knots in S3 will give you different tree manifolds. At least for simple examples, we can show that topologically equivalent three manifolds will give you the same Z of M, and topologically inequivalent three manifolds in many cases will be different. Okay, that's why it will be called as a three manifold invariant. Otherwise, you cannot call an object as a knot invariant or a three manifold invariant if it, if two equivalent knots give two different answers, then it is not a knot invariant, right? So you need to make sure that two equivalent objects, two equivalent manifolds or two equivalent knots should have the same three manifold invariant or same knot invariant. Okay, so that's the definition of an invariant. Okay, we will see it later that two equivalent manifolds, two topologically equivalent manifolds will have the same Z of M. Okay, so that is to answer one of the questions somebody asked. Other one, someone is asking why slicing. This is one of the ways in which he is trying to reproduce. Witten has tried to reproduce the skin relation of Jones polynomial for the SU2 group with fundamental representation placed on it by using this methodology. Okay, so this methodology helps in getting back all your polynomial invariants for knot. You can do perturbative, you can do summable by the total summable answer will come from this method. And to order by order up to certain orders, you can compare that perturbative answers matches with this side. Okay. Is that answering your question? Yeah, why can we slice the diagram? So this is why it is done. See, I'll just give you a little more insight in a different context. You all know Gauss's theorem, right? So you know that if you do the flux evaluation in a volume, you can also get equivalent information from the surface by doing E dot ds, right? Del cross E integrated over a volume. In some sense, if when you slice it, these punctures carry all the information about the bulk. Okay. So this is what happens, that and the exchange between punctures is actually a twist, overcrossing and undercrossing twist, which are shown inside the bulk of this 3 ball with an S2 boundary. If I exchange these two punctures twice, that information is encoded in the boundary theory. Okay. So what I'm trying to stress is that you can do a functional integral of Chern-Simons on this, on the extreme left, can be equivalently done as functional integral on the upper half 3 ball with an S2 boundary, and a functional integral of the lower 3 ball with an oppositely oriented S2 boundary. And you can take the inner product in some sense, and you will be able to get the expectation value of the Wilson loop operator for the trefoil, the answer. So these are two ingredients which helps us to get the summed up value is what I would like to tell you. Okay. Okay, so this is what I've explained here. Chern-Simons path integral on a 3 ball with 4 punctured S2 boundary. This I'm quoting from Witten's work in 1989, where you can look at the 4 punctured S2 boundary, where you can look at a conformal field theory on that 2-dimensional space. And because it has 4 punctures, you can associate a state which belongs to that conformal field theory, which is specifically this Vesuvino conformal field theory at level K. And you can treat this to be, because it's 4 punctures, it's a 4-point conformal block. So you can write the Chern-Simons functional integral on the upper ball with the boundary which has 4 punctures as a state psi which belongs to an Hilbert space. And the dimensionality of the Hilbert space will depend on representation R and also what gauge group we are looking at. Okay. So the dimensionality of this Hilbert space depends on the representation. I'm confining to SU2, so that's why I'm not saying about the group, but it also depends on the group in general. So for fundamental representation, what you can do is you can put fundamental representations on all of these punctures. Okay. And if you take a tensor product of the fundamental representations on all of these punctures, you can count how many singlets you can get, how many possible singlets you can get, and that turns out to be 2. Okay, because ultimately the total tensor product of all the fundamentals which you put in should give me a value which is as if it's a net charge being 0. Okay, so that can happen in 2 possible ways. Okay, so you can have tensor product of fundamental giving symmetric and antisymmetric. Similarly, this can give you symmetric and antisymmetric. Both being symmetric from here and symmetric from here can give you 1 singlet. Similarly, antisymmetric and antisymmetric can also give you 1 singlet. So in that sense, the number of singlets which turns out for fundamental representation is 2. I'll leave it you to check if you put spin 1, how many singlets you can get. It will turn out to be 3. Okay, please check it out. So that decides for you that the dimension of the Hilbert space for the fundamental representation is 2. Why am I stressing the dimension of the Hilbert space? The reason is that once you know the dimension of the Hilbert space, any linear combination of 3 states in a 2-dimensional Hilbert space will be set to 0 because they all cannot be linearly independent. Okay. This is all is what he has used. Witten has used this, such a simplest argument. Using the ingredient raw every knot as a closure of braid or plait of braid, and then use the fact that Chern-Simons functional integral on a 3-ball with punctured boundary. Specifically, he has taken the simplest example with 4 punctured boundary, associated a state in a Vesumino conformal field theory with the current algebra symmetry. Specifically, in this particular SU2 Chern-Simons, it turns out that the conformal field theory is SU2K Vesumino conformal field theory. And then exploited the fact that the state belongs to a Hilbert space whose dimension is dictated by what representation you are looking at. If you are looking at a representation which is fundamental, then it is going to give you number of singlets you can get is only 2 possibilities. So the dimension is 2. For such a vector space, a linear combination of 3 states have to be 0. Okay. So this fixes for you that I have taken only the upper ball, and once I take the upper ball, I have to glue it with a lower ball, and the lower ball states are typically taken to be a dual vector state, which is denoted by a bra of a chi. Okay. So this is what I've shown here. And claim is that inner product of the dual state with the state formally should give you the information about the knot invariant. Okay. And I can use the above relation to put the chi here, and chi here, and you'll ask what is psi 1 and psi 2. Okay. Formally, the way it is written is take psi to be having an overcrossing, psi 1 to have an undercrossing, and psi 2 to be a no crossing. And you can also write an undercrossing by saying that I apply exchange operator, the braiding operator, inverse twice, and then no crossing is like braiding operator inverse, and you get a characteristic equation for the braid operator. I'll go through this detail in the next lecture for you. Okay. And ultimately from this, we can just taking an inner product with chi on this equation, you'll end up getting L plus, L minus, and L0. And what these coefficients are dictated from the braiding or monodromy matrices of this conformal field theory, where these will be, one will be a sum of eigenvalues of the braiding matrix, the other one will be a product of eigenvalues. And you end up getting, you reproduce this skein relation between overcrossing, undercrossing, and no crossing, which I said in the beginning of the lecture. Okay. And whatever I've said here for fundamental of SU2, you can do the same thing for fundamental of SUN. Again, the Hilbert space dimension turns out to be 2 for that. And there is a two variable generalization in knot theory called home-fly PT, where these set of authors have independently found a variation with two variables introduced instead of one variable. And those invariants are home-fly PT polynomial, and that can also be obtained by the same logic. Okay, only the coefficients are going to be now dependent on not just SU2, but also the rank SUN. Okay, so that's the modification. I'm not going to do that, but it can be. You can go back and look at Witten's paper, and you'll be able to appreciate that the same skin relation can be obtained. Yeah. Okay, so there's some questions. I can answer this question and then stop here, Daniel. Okay. Yeah. Did we find anything new about SU2 group properties once Witten got Jones polynomial from 3D and relate anything from knot cohomology stuff to SU2? I am not sure whether basically Witten did only for fundamental representation, but this procedure could be done beyond fundamental. We tried to do this for in 1992 our paper. We tried to do it for spin 1 or general spin n representation, and also we found that the skin relation is little more cumbersome because you need to know lower crossing invariant to dictate and find what is the higher crossing invariant. So we exploited these two properties which Witten had proposed, and we devised a method to get the invariance directly. Okay, so those are the new things which we did, and it was really powerful because given any diagram, I don't need to go through the skin relation, but I can compute everything about the knot polynomial, at least for the SU2. Whether it's related to knot cohomology stuff, I'm not sure, but probably there were many other variants introduced by Kono on homology and so on. Those came up only in the turn of the century. Okay, around 1999, 2000, there were some interesting work on homological invariants.